Okay, so these are the notes on 2.1 to 2.3. So what is a tangent line? So if you notice, tangent lines touch a curve at one point. All of these are tangent lines, even though it goes through the curve here, because the tangent line is a line that is the same as the slope of the curve. So although many times we might say that a tangent line drawn to a curve may only touch the curve at one place or one time, that's not always true. Secant lines are by definition a line that intersects a curve at least twice. So we're going to come down here and look at some misconceptions that we have about tangent lines. So the formal definition of tangent line looks like it's often problematic. The following four misconceptions can be helpful when deciding whether a line is tangent to a curve. Misconception one, a line is tangent to a curve if the line crosses the curve exactly one point. Although this line L touches the curve C at one point L, line L is not tangent because it would have to be touching the curve at the same slope as the curve of the function. Coming over here, another misconception is a tangent line can only touches a curve once. When we're talking tangent lines in here, we're talking about just in this area. So we don't even worry about this part of the tangent line. But if we took it on out, it could touch the line more than once. But we're trying to find the curve or the slope of the tangent that's going to be the same as the slope of the function. Going on to the next misconception. Up here again, a line of a curve touches a line once, but does not cross the curve. So this is not a tangent line because it wouldn't be a line, it'd be a segment, okay? So it's still not a tangent line because it's not in the same slope as the curve is sloping. And then again, another tangent line myth is it's a curve is a line, a tangent to a curve is a line that just grazes the curve at a point but does not cross the curve. Again, if you look right here, this thing's crossing, but we're more worried about just this part of the tangent where the slope of the tangent will equal the slope of the curve. So the tangent line problem says begin with a graph y equals f of x. So that's this graph right here. And it says let's begin with an arbitrary point, C, F, F. That point is this one right here, C and F of C. You plug some C in, you get F of C out. And it says now let's find a new point, x, F of x, and place that point on the curve close to the right edge. So I'm going to come over here and I'm going to say, hey, this point right here is going to be x and F of x. It's going to be this point right here that I just drew in red. Place this point in your curve close to the right edge. Connect those points. What is the slope of the secant line? So in other words, if I took a line and I could draw straight through these 2 points here, I want the slope of that line. So the slope of the secant, I'm going to put SEC for secant, is going to equal, I hope we all know that that is going to be the change of the y's over the change in the x's. So that's the equation of the secant line right there. And now we're trying to get this to become a tangent line. So we're going to move the point a little closer. We're going to move that point a little closer. And it says about halfway. So I'm going to take this point and stick it in here somewhere. And say, now this is x and f of x right here. So now my secant line is going kind of like that. So now, is there different in the way we calculate the slope? And the answer is no, there's no difference. And do we still see a secant line? Yes, we still see a secant line. So we can still say that the slope of this new secant line is going to be exactly the same as it was up there, except my x and my y would be different values in a real problem. But I still have this slope. Now, as you can tell, this secant line slope is a little higher than this secant line, but we're getting closer to the tangent. And then step 3 says, since we are having such a blast moving our second x value closer to the C, let's move the x value so it almost touches C. So we're going to take x, f of x, so that it's right next to C and connect the 2 points. So if I do, here is that first point, I'm just going to say I'm going to put it right here beside it. I'm going to draw that secant line. Well, do we still see a secant line? Probably it's going to be kind of hard to see because I'm so close to it. But actually, there still would be a secant line there. So how could we perceive the slope using very important concepts from Unit 1? Well, if we were saying that this distance here, a distance right there was being our distance from C to X, and then I hope we see that distance from C to X is getting smaller and smaller until we get almost to exactly the same point. Well, that's what we were doing before. But now we're finding the slope of the tangent. We're going to say that the slope of the tangent is going to be the limit as that X value out to the right approaches C. It basically becomes, that X that was out there is going to become the C. So that will be the slope of the tangent line, which is going to still be the limit of the regular slopes we did before. But it's not going to be exactly on the C. C and X will not be exactly, but we're approaching so close you're not going to be able to tell the difference. So the definition of a tangent line with a slope. So the definition is going to be, move that back up a little bit, sorry. If f is defined on an open interval containing C, and if the limit is this, is that deal we just found, exists, then the line passing through the point C, CF with the slope M is tangent line to the graph of f at the point C, f of C. So in other words, we're basically trying to say we're making at the same point. So this says the slope of a graph of a linear function, find the slope of the graph of f of x when x is 1. Well, there's a way in calculus we write slope. So we call it f prime, because this is f. F prime of x is a way to write slope. As we'll find out in a few minutes, that's also known as the derivative of f. So this is going to equal the limit as x approaches 1, because we're coming to this 1 value right here. And then that's going to be of the function, which is f of x. So I'm going to put 2x minus 3 in there, because it's the same f of x that's here. But I'm going to go ahead and plug in what f of x equals. Minus, and now we're doing f of 1. See that this x equals 1, this is f of 1 here. So we're going to actually stick 1 in for the x. And then that's going to be over x minus 1. So when we do all this simplification here, let's see, we're going to get 2x minus 3, and then this is going to be negative 1, so that'll be plus 1. So this will end up being, oops, I left off the limit. We got to keep the limit on there, sorry. The limit as x approaches 1, and then we're going to have 2x minus 2 when we add our like terms over x minus 1. So now if we plug 1 in there, I hope we see that the top goes to 0, the bottom goes to 0. So we just learned a little while ago that we can fix this. So we can factor out a GCF in the top of 2. And now we can reduce our x minus 1s, and the slope there would be a 2. So the limit as x approaches 1 of 2 is 2. That's one of those properties we had. Now this says find the slope of a tangent line for this function where x equals 1. So we're going to do the same thing. So we're going to say f prime of x is going to equal the limit as x approaches 1. And then now we got a new function. Now we got x squared. I think that's squared. Yes. We got x squared plus 1 minus. Now we're going to stick the 1 in there. We want to stick this 1 in there. So we're going to get 1 squared plus 1 all over x minus 1. So we're going to combine like terms again. So we're going to have 1 and 1 is 2. So that's going to be, keep the limit on there as x approaches 1. And we're going to have x squared minus 1 all over x minus 1. And we plug 1 in, we get 0 again. We plug 1 in, we get 0 again. So we have to fix this one as well. Now we have a difference of squares on top. So we factor the x plus 1 and x minus 1. And then we have over x minus minus 1, so those x minus 1s reduce, and we stick our 1 in, so this slope is also 2. So I'm going to stop there because I got a class coming in, and then I will finish these notes up and put them out later.